Hi everyone and welcome back to PrepFusion. I am Anish and today we will start with the lecture 28 of our electrical machines subject, right? So today we will discuss about armature winding. So previous lecture we discussed about all the parts. In those parts armature winding was also one of them, right? We discussed about the definitions of different parts, what are the importance, few terms as well we discuss. So today we will dive more deeper into armature winding. Also we will discuss about equivalent resistance and voltage across the armature. So if I connect the winding, what will be the equivalent resistance and voltage? Also we will discuss about lap and wave winding, which is a very important um, types, which are very important types of winding for armature in a DC machine. Also we will discuss about brushes, right? What happens if I remove few brushes, what are brushes actually used for, those things also we have discussed previously as well. Today we will discuss more about those. So first is the armature winding. So previously also we discussed classification of armature winding, open winding, closed winding, right? Armature winding has multiple kind of classifications. This is also another one of them, that single layer winding and multi-layer winding or double layer winding. So what does single layer winding means? Single layer winding very simply means that I have these slots, right? In each slot I will have one coil, only a single coil. In each slot I will have a single coil, that's it. Okay, in case of single layer winding, in each slot I will have a single layer only. Okay, so what will be the total number of coils? Because I know if this is one of the conductors, the other end of the conductor will be somewhere here, right? Or somewhere here, somewhere here. So a coil is made from two conductors. A coil is made from two conductors, correct? And each slot will contain one conductor. So sorry if I mentioned something else, that each slot will contain one coil, I was wrong, sorry. I wanted to explain that each slot will have a single conductor. Each slot each slot will have single conductor. Okay, now how many coils can each slot have then? So each slot has single conductor, I know, and I know two conductors make a coil. So how many coils will be there? So it will be basically total number of coils will be what? Like one conductor contains one coil contains two conductors. So one conductor will contain 1 by two number of coils, right? So basically then the number of slots will be equals to the number of coils, that is n divided by 2. Okay, or sorry, number of coils, yeah, you can write this as c divided by 2, c divided by 2, right? C divided by 2. Am I correct here? Okay, something I've messed up. One single conductor is there. No, it is correct only. Number of coils. Okay, what am I messing up? Something I'm doing here. Single conductor. I have a single conductor. Single conductor means how many coils it is? Yeah, half of a coil only. Yes. So each slot will contain a conductor. Then how many number of coils I will have? If I have this many number of slots, I will have half number of coils. That is correct only. So sorry, each. So single conductor is equals to a slot, correct? So number of conductors is equals to number of slots. So number of slots is equals to number of conductors, right? So I can say here that the S, right, S will be equals to the number of conductors, Z, right? And what is basically, so this is Z, and what is another relation, that Z is equals to like I know number of coils, uh, so 2 into Z, sorry, Z by 2 is basically the total number of coils, right? Am I correct? So if I have two conductors, then I will have a single coil, correct? Two conductors means this and this, this and this. So it will provide a single coil, correct? So I can replace a Z with S, right? So I can directly write here. So my S by 2, slots by 2 will be the number of coils. So basically in case of single layer winding, the coils, number of coils will be equals to slot by 2. Okay. In each slot, single conductor will be there. So same like example calculation is there. Now to actually this is very simple to manufacture but very poor space utilization. Only a single conductor is there, right? So we use multi-layer winding such as double layer winding. So in double layer winding, each slot will contain like two coil sides. Each slot will contain two coil sides, right? One in the top half, other one in the bottom half. So this will contain like this YOLO is a whole coil, right? So one side of the coil will be placed in the bottom, other side of the coil will be placed at the top. That's how we place the conductors to maintain symmetry. Okay. So now the number of coils and number of slots will be equal. Number of coils and number of slots will be equal. Why? Because each slot has two coil sides. That's why overall how many coils I have? One. You can see this is yellow. Yellow is one. Then I have pink, two, blue, three, and this orange one, four. Right? How many slots I have? Four. So in this case, in case of double layer winding, number of coils and number of slots will be same. Okay. So this was the example calculation. You can see the number of slots and number of coils. So each coil has one side placed in the top layer of the slot and the other side is bottom layer. This enhances the mechanical rigidity, improves heat dissipation and optimizes the slot space. Because we're using like the space very well, we are carrying more coils, so more EMF will be induced. That is better. So now let's discuss another type of winding, that is lap and wave winding. Okay, so most important portion for lap and wave winding blindly is you have to remember this, that number of parallel paths will be equals to the number of poles. Okay, what do I mean by it? I will explain. But this thing you have to remember, very important, right? For lap winding and for wave winding, the number of parallel paths will be 2 no matter what. Okay, what is lap winding physically? Physically, lap winding basically means the end of each coil will be connected to the start of the adjacent coil. Just like here, if you see, this is the end of the red coil, right? So it is connected to the start of the coil 2. So basically, what is happening? So here as well, end of one coil is connected to the start of the other coil. Here as well, end of one coil is connected to the start of the other coil. Here as well, same thing. Here as well, same thing, right? And the number of parallel paths will be equal to the number of poles. So this is a 4-pole machine. That's why there are 4 brushes. So number of brushes will be equal to number of poles. In case of lap winding, number of brushes will be equal to number of poles. As it is a 4-pole machine, I will have 4 brushes. And how many parallel paths I have? So if you notice, okay, this thing is still there. If you notice one thing, that here, right, this is my coil and let's assume it is a generator. So if it's a generator, then it will supply the power, right? So current will leave from the positive terminal. So 4 volt is here and 4 amperes is here. So current leaves from the positive terminal. So what I can say is that as current leaves from the positive terminal, how many parallel paths I have? So this 4 amperes is coming over here. I can use some other color. This 4 amperes is coming over here. This 4 amperes is coming over here. So overall, it is one of the parallel path, right? So two parallel paths. These are two parallel paths. So these two are combining here, coming here. So these two are the parallel paths. Again, if I see, again same thing, right? Again, basically from this point, 4 amperes will leave from this positive terminal. 4 amperes will leave from this positive terminal. So this will be 8 amperes. This will be 8 amperes. Okay, so 8 amperes will leave from here, 8 amperes will leave from here. Again here, right, this is another parallel path, right? Again these two are the parallel paths. So these two are the parallel paths, these two are the parallel paths, right? For a single side, I mean, I'm just talking about the positive terminal. I see 4 parallel paths. These are the 2 parallel paths. These are the 2 parallel paths. Parallel paths. and these are the two parallel paths. Okay, so overall 4 parallel paths I have as discussed here, right? I will have 4 parallel paths. So this is lap winding, and lap winding is generally used for low voltage high current. I will explain why. Let's discuss wave winding. So wave winding, it is fixed irrespective, number of parallel paths is fixed, that is 2, and number of brushes also will be 2. So here again the same thing, right? 4 amperes current is leaving from here and 4 amperes current is leaving from here. So how many parallel paths I have? Only 2, right? So because here, right, I did not, this is just like the negative terminal. For the positive terminal I have only 2 parallel paths. So number of parallel paths is 2 only here. Now let's discuss what is the current that I am providing and what is the voltage rating. So if I see current, I am providing 8 amperes because 4 ampere is 8 amperes. So voltage, if I see, all these are single coils, right? So like number of conductors is same. Here I have 4, here I have total 8 conductors, number of conductors. Here also I have total 8 number of conductors. Okay, each conductor is 4 volts. So what is the voltage? If I just simply apply a KVL, I will see the voltage in this wave winding is 16 volts. In the lap winding it is 8 volts only. If you apply KVL, you will see it is 8 volt only. What is the current? So here 8 amperes is coming, here also 8 amperes is coming. Okay, so overall the output is 16 amperes. Overall the output is 16 amperes. Okay, so I see here the current is 8 amperes, voltage is 16, current is high here, voltage is low. So why? Because I have more parallel paths. So although the maximum rating of the coils are fixed, but as there are more number of parallel paths, individually they can contribute more current. So that's why lap winding is used for low voltage high current applications and wave winding is used for high voltage low current application. This is the physical reasoning behind why lap winding and wave winding are used in what kind of cases. Okay, so motors I will not discuss, generators I am just discussing. Okay, so this was the feature. Now why is it called a lap winding? Why is it called a lap winding? It is called a lap winding because uh, basically in the diagram the winding laps over the other. So if you see in this developed diagram, right, one of the winding or one of the coil laps over the other coil. As it is lapping over the other coil, that's why the name lap winding. Very simple. And in here, as it is like a wave, that's why it is called a wave winding. Why is it called a wave winding? Because the winding diagram, because the winding diagram is just like a wave, that's it. Because the winding diagram is like a wave. Okay, so yeah, uh, so I hope you have understood this particular things, what is lap winding, what is wave winding. Now there is another thing known as dummy coil. Okay, dummy coils are unused coil inserted in the vacant slot. So few slots in the armature may be vacant and we might just place the coils. Those will not be used for inducing the EMF, those are just placed as a placeholder. So those are called as dummy coils. Okay, they maintain the mechanical balance but do not participate in energy conversion. Okay, commonly used in wave windings where slots are odd. I mean, if slots are odd, generally they are used in wave winding. Okay, now let's discuss about the problem of circulating current in lap winding. Okay, what is the problem of circulating current in lap winding? So in lap winding, as there are multiple coils that are connected in parallel, even if there is slight change in the voltage levels, right, of the coils due to some problem, due to unsymmetry, or like one of the coils has just 1 turn more or 1 turn less, then it will induce more voltage. So due to that, there can be a flow of circulating current. So in this first circuit, right, there is no problem. In the first circuit, there is no circulating current. Like as these voltages are same and these resistances are also same, so I can convert this into equivalent voltage source, right? This will be 4.5 volts and this will be 0.1 divided by 4 basically. I can use the Miller's equivalent, right? Okay. So all this is fine. Now here what is the problem? Here we have a problem. As there are more number of parallel paths, right? Even if there is, just say this is 0.1 volts higher than the actual 4.5 and this is 0.1 volts lower, what is the problem? Problem is, let's assume that the equivalent voltage that we get at the output is 4 volts. Okay, that is the assumption. If it is 4 volts, what is the current that is coming out here? So what is the current that is coming out from here? So current that is supposed to come out from here, right? It is basically equals to 4.5 minus 4.5 divided by 0.1, that is 5 amperes. Okay. Now what is the current coming out of from here? The current that is coming out from here is 4.6 minus 4 divided by 0.1, so it will be 6 amperes, right? So if my coil rating is supposed to be 5 amperes only, it cannot pass more than 5 amperes of current, so it is passing more current. Okay, so coil can get damaged. And basically now how much current will this supply? This will supply 4 minus 4 divided by 0.1, this will supply 4 amperes of current. So there is bit of disbalance of current, right? This is supplying 6 amperes, this is supplying 4 amperes. So basically what will happen, ideally this will not be actually 4 volts. Ideally, in reality this will not be 4 volts. Okay, in reality this will be something else. So what will be the problem basically is, I have already discussed in transformers as well, right? If I have two voltages which are of different voltages, okay, and I want to connect them in parallel and there is a resistance in between, there will be circulating currents. This we have already discussed, right? So we don't actually want this, right? We don't want this circulating currents. Circulating current is a huge problem for us. So that is what is written over here, that in lap winding each parallel path connects a different segment of armature winding. Due to asymmetricities in magnetic field distribution, differences in armature resistance or unequal brush contacts, the induced EMF in different parallel paths may not be identical. They may not be identical. Okay, this leads to formation of circulating currents between these paths which do not contribute to useful power, right? Circulating currents can flow in the coils just like transformers, right? Okay, not again doing the same calculations because I have already done it in transformers. Okay, so these are the problems. Can cause brush overloading because through the brush, right? These are the brushes basically. There is a limit, maximum rating of the current that can flow. If huge high amount of current is there, then the brush can get damaged. It can cause local heating because more copper loss will be there. If this is supplying more current, more copper loss here. Reduce efficiency, of course. Accelerate the brush wear and tear because of course high current is flowing, the brush can get damaged much easier. Okay, so that's the difference basically. I hope you have understood. So here no circulating current flows, no circulating current because all the voltages are same, right? But here even if there's minute difference, so in reality circulating current will flow, circulating inside the supply, right? So circulating current is like this will flow, circulating currents will flow. Okay, so effects I have already discussed, increased copper loss, all these things will happen. What is the solution? Solution is, we have a thing known as equalizer rings. So what does the equalizer ring do is, they try to connect these 2 points, okay, and they try to maintain the potential same. So I'm just not explaining technically, I'm just explaining what is the solution. Solution is, we use equalizer rings which can maintain the potential here so that no circulating currents flows through the coils. Whatever circulating current will flow through the machines only, they will not flow through the brush. So that is the solution of whatever we have discussed. Okay, this is what these are called equalizer coils or equalizer rings. So you can see we are just connecting these two, shorting these 2 points so that whatever circulating current is flowing, that is either flowing in this loop, it is not flowing through the outer coils, right? We have some protective circuit there, so that can allow the circulating current to flow. Okay, so that is the advantage of that is the solution of whatever we discussed. And now wave winding. Why does wave winding does not have circulating current? In wave winding, every parallel path covers all poles uniformly because I have only 2 parallel paths, right, and they will cover uniformly almost. So there is a very less possibility of circulating currents, because the number of parallel paths is already low, it is only 2, right? So very less possibility of circulating currents. So these are the basically differences between the lap winding and the wave winding. Most important difference is this one, right? The number of parallel paths, because this will be used to derive the expression of the induced EMF. Okay, so yeah, you can go through the differences. So now one more classification of armature winding is complete and incomplete winding. So what is complete winding? In complete winding, all the slots will be fully utilized. Okay, each slot will contain active coil sides. Slots means, I hope you know, right, the inside part. And in incomplete winding, some slots will be intentionally left to meet certain design criteria or constraints, right? So those slots can be either filled with dummy coils or those can be left empty. Okay, to maintain rotor balance, those slots shall be filled with dummy coils. In here, no dummy coils are required, but in incomplete winding, dummy coils will be required. Okay, so and in incomplete winding, equalizer coils are also not required, since electrical symmetry is not expected. There is no risk of circulating current in unused coils. Okay, so already few slots are empty and those slots will not be connected, so there is no possibility of circulating currents there. So we don't use equalizer coils there, we use equalizer coils in complete winding only. Okay, so one more thing is there about multiplex winding. What is multiplex winding? So if I need more number of parallel paths, what I do, when current requirements are very high, the number of parallel paths needs to be increased beyond the default. This leads to multiplex winding configuration, where windings are split into multiple independent layers. So now the number of slots also has been increased, right? Or number of layers has been increased. So I told you, right, double layer, single layer winding. So number of layers have been increased. So in each slot, the number of coils sides will increase. Okay, number of layers okay, number of layers has been increased. So it depends, right? If it's a duplex winding, so like in lap winding, normal simplest lap winding, number of parallel paths equals to number of poles. In duplex lap winding, number of parallel paths will be 2 times the number of poles, because it is a double layered, right? It is a double layered, so number of parallel paths will increase. Okay, now if it is triplex winding, number of parallel paths will be 3 times p. So I need higher current rating, right? So I have to increase the rating, so that's why the number of parallel paths has been increased. So these are the examples, I hope you can see, where like generally the formula is A is equals to MP, where the number of parallel paths is equals to M times the number of poles. Okay, that is what my number of parallel paths is equals to. Okay, in case of wave winding, if I want to use multi-layer, so in case of wave winding, right, I always have the number of parallel paths. In case of simplest wave winding is equals to 2. For duplex it will be 4, because I will have 2 layers. For triplex it will be 6, right? So basic formula is A is equals to 2 into M, where M is the this multiplexing factor. Okay, same thing, right? Unless and until specified, you will always assume anything as simplex wounded, whether it be it lap winding or wave winding, you will always assume it to be simplex wave wounded. So let's now discuss how if will be the equivalent induced EMF formula. So before that, few design insights. So lap winding we have already discussed that it will be used for low voltage high current applications. Wave winding will be used for high voltage low current applications. Okay, but trade off is we will need equalizer rings to combat the circulating current. Okay, wave winding is used for high voltage low current application. So now let's derive few values for whatever we have been learning. Right now we will derive the expression for induced EMF in a DC machine. So this discussion is the most important portion. Please listen to this discussion very carefully. So let's say I have a orientation or a circuit, right, which is, let's say, lab bonded, and I have these many amount of coils in series. So C is the number of coils connected in series in each parallel path. okay, and I have total A number of parallel paths, right? A is the number of parallel paths, and NC is the number of turns in each coil, okay, and R is the resistance per conductor, and Z is the total number of conductors. Okay, these are the values, and EC is the induced EMF in a single coil. Okay, so then what will be the expression for R equivalent of this whole circuit and the whole induced EMF? So what I can comment is the R equivalent, right? R equivalent will be what, for me to find the R equivalent, all these are in series and then they are in parallel. Okay, so before that I want to write what will be the total number of conductors equals to. So I know that I have, in each parallel path I have total C number of coils, and I have A of these parallel paths. So how many coils I have? A into C. Total number of coils is, in each parallel path I have, let's take an example. Let's say I have two parallel paths, and in each parallel path I have two coils. So how many total number of coils I have? 2 into 2, 4. So same thing, total number of coils will be C into A. Total number of coils will be C into A. Okay. Now, these are my total number of coils. Now, how many conductors do I have total? So, if these are my total number of coils, and in each coil I have NC number of turns. So, how many total number of turns I have? NC into C into A, right? These are the total number of turns. Now, if I know these are my total number of turns, how many total number of conductors I have? Because I know that each turn will have two conductors. Each turn will have two conductors. So if I have two turns, then how many conductors I have? 4. If I have NC into C into A turns, how many conductors I have? 2 into this, right? Twice. So this will be 2. So this will be my value of Z, right? This will be the value of Z. Okay. Now same application I will do here. Okay. Same application I will do here. So here, right, all these coils are in series. So what is the resistance of each coil? So there are many turns, right? And if, let's say, this is a turn, this is a turn, just hold on, and next again I have another turn, correct? So basically I have two turns here, and I know the resistance per conductor. So I have one conductor here, one conductor here, one conductor here, one conductor here. So I have 4 conductors here, right? So these 4 will be in series or parallel? These 4 will be in series, because if you see current flowing through here, same current is flowing through here. So all these 4 conductors are in series. So if I am able to find out the resistance of a coil, so first let me calculate the resistance of a coil. So this I will come to later. Let me write this will come later. Resistance of a coil. So what is the resistance of a coil? So resistance of a coil, let me name it as RC. This will be equals to, here, total the resistance per conductor is R. So here I have 2 turns. So what will be the total resistance? 4R, right? 4 conductors I have. So I just need to find out the total number of conductors in each coil. What is the total number of conductors in each coil? In each coil, not in every parallel path, in each coil. It is 2 into NC, correct? Total number of conductors in each coil will be the number of turns into 2, because each turn has 2 conductors. So in each coil I will have 2 into NC number of conductors, and each conductor has resistance R. So 2 into NC conductors will have resistance of 2 into NC into R. Okay, so they will have 2 into NC into R. Okay, so this is the resistance of each coil. Now how many coils are in series? C number of coils, right? C number of coils are in series. So the resistance of one path, resistance of one path, let me name it as RA, will be what? It will be C into RC, right? Total number of coils in series into RC, because each coil has resistance of RC. So this will be 2 NC into C into R. Now what do I know? Now I know that what will be the overall resistance, because each path, so now right now the diagram will look something like this, right? I will have RC here, CRC here, then CRC here, and this will go on like this A times, right? A paths. So what they are just connected in parallel. So I will just divide them by A. So if two resistance of equal value R are connected in parallel, what is the equivalent resistance? R by 2. Same thing, if CRC is connected in parallel A times, it will be CRC divided by A. So this will come out to be the resistance R equivalent will come out to be CRC divided by A. So this will be equals to 2 into NC C into small r divided by A. Now I don't like this small c, right? I don't know all these parameters. So what I will do, I will multiply and divide by A, because why? Because I know this value, right? I know 2 NCC into A is Z. So I will multiply and divide by A. So this will be 2 NC C into A divided by A square. So from here what I can say is that this value is what? This is Z, right? This value is Z simply, right? So I will just replace this with Z. So this is the expression for R equivalent. Now I don't want you to mug this one up. The induced EMF, yes, you have to remember that, but resistance, this can be solved using concepts, right? So I want you to go through the method, the process, right? So I don't want you to mug this up, because someday they will change the value, right? Maybe they will change this definition. Maybe the R is not the resistance of a single conductor, maybe it is something else. Okay, just maybe it is something else, right? Maybe R is not the resistance per conductor, maybe it will be resistance per coil. So please understand the process. If you understand the process, then even if any term here changes, you will be able to derive the values. Okay, that is the most important portion that I want to focus on. So here R equivalent will be equals to Z upon A square R. Now remember, whenever you are using and making short notes here, right, remember which term is what, right? What is which term? So always remember that, remember this. I know gate will trick you one day. Gate will trick you that this R, remember, is resistance per conductor. If the definition of small r changes, then the formula also will change. So please keep that in mind. Okay, now let's derive for the voltage, induced voltage, right? So this is done. So let me find out what is the voltage induced in a single coil. What will be the voltage induced in a single coil? Okay, so EC, right? If my flux equation is something like this, and I know rectified flux will be something like this, right? Rectified flux will be something like this, or rectified induced EMF, right? The waveform will be something like this. So its average value will not be 0, okay, because I am commutating it. I am using commutators. So if I write what is my EC, instantaneous value of EC, so I will write a small EC T. It will be d phi n d phi dt, right? For a coil, NC into d phi dt. So this will be NC into d phi of t over dt. Okay, so this value will be NC into d phi over dt. So phi mp is the basically peak flux per pole. Peak flux per pole. Okay, so NC into phi m peak to peak, and omega will be there, and this will be cos of omega t, whatever this value is. So anyways, I will be rectifying it. So if I will be rectifying it, what will be the EC average? Because that is what I am interested in, right? EC average. It will be, what is average here? If this is the peak, right, it will be 2 into ECM upon pi, right? We know this, the average of any rectified sine wave. Okay, so this will be 2 NC, the peak value, MPP flux per pole, divided by pi. Okay, so this is the induced EMF in a single coil. So this is the induced EMF per coil. Now, what is the overall induced EMF? E, right? It is just C into EC, because I have C coils connected in series with each other, right? So it will be C times EC. So induced EMF of the armature, induced EMF of armature. So that is equals to E equals to C into EC, right, which is equals to C 2, okay, omega is also there, sorry, omega, remember this is omega electrical, right? Whatever we are discussing, it is electrical radiance, okay, omega electrical. So this will be 2 NC phi MPP omega electrical divided by pi. Okay, into C. Now one more thing, one more relation, we have already proved that my omega electrical is equals to P by 2 omega mechanical. This we already have proved. Why do I want to bring omega mechanical? Because I know what is my omega mechanical. This also we have proved. It is 2 pi n by 60, where n is the revolutions per minute. I just wanted to get this formula into a standard form, so that's why I have to do all this replacements, right? So now one more important thing, what is NC into C? What is NC into C? So NC into C, right, if you see here, NC into C is Z upon 2A. So from here I can write NC into C or CNC equals to Z upon 2A, right? So I will replace it. I will replace Z upon 2A here. So this value will be equals to 2 NC into C is Z upon 2A, Z upon 2A, phi MP, I will just write phi here, okay, just for the sake, but remember this is the flux per, peak flux per pole, okay. Now this will be omega E will be replaced with P by 2 into omega M, omega N is 2 pi N by 60 divided by pi, okay. So few cancellations will happen here, so this 2 and this 2 can get cancelled, okay, let me not cancel it directly here. This 2 and this 2 will get cancelled, this 2 and this 2 will be cancelled, only 60 will be left, that will go down, pi will get cancelled. So at the top I will have phi Z and P, at the top I will have phi Z and P, phi Z and P, and at the bottom I will have 60 into A. Okay, this is the beautiful formula that I know you guys have already studied or you will study, right? Everywhere else you will see this, but now I hope you know the derivation. Okay, the derivation also you know how we got to this value, right? Very important and elegant result. This is now most important value. This is okay. Remember, this will be the induced EMF only if the flux is assumed to be sinusoidal. If it is flat top, then the induced EMF might be different, right? Because then the average formula will change. But we assume everywhere else we use this, but nowhere we mention this, that this formula will be valid only if the flux is assumed to be sinusoidal. If it is not sinusoidal, right, this value will be something else. Sinusoidal. Okay, just be careful about this thing. Okay, this was about the formulae. So now I hope all those things previously, whatever I discussed, that my induced EMF if is proportional to the flux, is proportional to the speed. These are there. Also, I told you previously that it is proportional to the number of conductors, it is proportional to the pole, and inversely proportional to the parallel path. So previously I did not use this because at that point of time you did not knew what is parallel path. But all these terms I have already told you, but I did not write the formula there, right? Because this was the right time to discuss about the formula. Now one more doubt you might have, sir, I have this resistance, R equivalent I was able to write. What is my R equivalent? So R equivalent was basically your Z upon A square into R, okay, and your induced EMF also, sir, you have derived, it is 5Z NP divided by 60A. What about inductance? What about L equivalent? So actually L equivalent we don't need to calculate. We don't need to calculate L equivalent, okay, we don't need to calculate L equivalent. Okay, why? Because we are talking about average means DC. So as we are talking about DC, right? So as we are talking about DC values here, in DC your inductor will be short circuit because the average voltage across the inductor will be VL average will be 0, right? Hence we don't need to discuss about the inductor. Okay, now one more thing, what about the torque then, sir? So what will be the torque? Will my torque be affected? Now you might have a doubt, sir, this waveform, right, this induced EMF, okay, it is pulsating in nature. So this will have a DC component and a AC component, correct? So let me write the DC and AC component, because this we have already proved that my electrical torque is proportional to flux and the armature current. I have derived this, right, previously. So I can write my developed torque, or developed torque I can write, developed torque will be equals to some K into phi m peak flux into the armature current. Now this armature current, because I have told you, right, armature current, because induced EMF is not alternating but pulsating in nature, so it will have AC and DC component, right? As my current is pulsating, so it will have both AC and DC. Okay, it will have both AC and DC, right? So as my current is pulsating. Okay, so if it will have both AC and DC, how the torque also will have its AC and DC. So torque TD also I can write, TD will be I phi m, it will have a DC component and AC component. Let me assume the AC component, this is the DC component, the average value IA DC, or the average, right? This is the average component of current, armature current, and I have a AC component. So AC component is plus K phi m IA AC. Let me assume the AC to be sinusoidal. Okay, it can have more harmonics, this waveform, right? This waveform can have more harmonics. I am just discussing about the fundamental component. This will have many harmonics, so I am just discussing about the fundamental component. So K IA1 sine omega electrical into T, and second harmonics also it can have, right? K into phi m IA2 sine omega into T, 2 omega into T. Sorry, this will be omega 1, this will be 2 omega into T, and so on. It will go on, right? Now, first of all, what is this? It is just like vibration. What do I mean by vibration? So let me give you an example. This is my phone, right? This is my phone. Now this torque, right? This torque sine omega t. it is alternating. So first, for the first half cycle it will be like this, then for the next half cycle it will be like this, right? First I will rotate this, this. It will just keep on rotating like this. So what does it feel? It is just like vibration, right? It is just like vibration. Now these means these components, like this is a constant torque. That means, let's say if I assume my torque direction to be clockwise, so it is a constant torque, so it will act in the clockwise only. So my phone will rotate in the clockwise only, right? But these torques are alternating in nature, alternating. So this will do what? This will provide vibrations, right? Vibrations, because you can see for the first half cycle it will be on the clockwise direction, next half cycle it will be anti-clockwise. Vibration, why? Because for the first half cycle it will be positive, next half cycle it will be negative. Positive I have assumed to be clockwise. I think from your end I guess it is clockwise only, right? So whatever it is, I hope you can understand. So this components, this harmonics will only provide vibrations. Now this is a very small object, right? Its weight will be hardly like 200-300 grams. A machine is like, I don't know what is the weight of a machine. It at least minimum it will be like 50 to 100 kgs, right? 50 to 100 kgs. Okay, that is no, not 50 to 100 kg, sorry, 1 ton, 1000 kg, right? Machine can weigh till 1000 kg as well, okay? Because my weight will be like I am very weak, right? I am very weak. You can see. That's why I was able to rotate this so easily. But let's say a 1000 kg object is there, and these kind of vibrations are happening. Will that object allow it? Inertia won't allow it, right? Because it is so heavy. You cannot just do this, right? You cannot just slight vibration you will feel. Other than that, you will not be able to absorb this torque. So due to inertia, due to inertia, basically nothing will happen, okay? Due to inertia, these will not do anything. So the ultimate torque is only due to the average value. So that's why we are concerned about the average value. So my TE average, or developed torque average, right, that is what I am concerned about, will be equals to K phi m into IA average. So that's why I don't care, right? That's why the inductor, right? I don't care whether the inductor is present or not present, inductance is there or not there, okay? But there is a concept of commutation where there is concept of reactance voltage, that is a separate thing. But here I don't care about the inductance of the coils. I don't care about the inductance of the coils here at this stage, okay? So yeah, I hope all of that is cleared basically. So yeah, that is what we learned basically. So things are written over here. So the total EMF will be each, so not E conductor, it will be E coil, right? This will not be E conductor, it will be each coil, induced EMF in each coil into the each coil into Z by A. Z by A is the number of coils in a single path, right? So this we have already derived. This we have already derived. I feel I don't need to like explain this anymore, right? So armature resistance also we have derived how all those values are coming up, okay? So yeah, one more classification is there about windings, this concentrated and distributed winding. So it is just a theoretical thing, you can go through and read over this, not that important, okay? For gate perspective, not that important. Yeah, now let's solve few questions, okay? So this is the first question. A DC generator with 4 poles has 100 armature turns with an EMF of 10 volt per turn, okay? So per turn EMF is 10 volt. So remember, that's why derivation is so important, right? That's why derivation is important. You cannot just mug the formula up, okay? So first of all, it has 4 poles. So now I will keep on writing the values. So it is a 4 pole machine. It is a generator. It is a generator. They have not told me whether it is a shunt series or a separately excited generator. I just know it is a generator. It is a 4 pole machine. It has 100 turns, 100 armature turns. So N, the total number of turns. It is not the turn per coil. Total number of turns is 100, right? N total, or I can just write T here, right? That will be better. Total armature turns. With an EMF per turn, EMF per turn as 10 volt. Okay. Current capacity is per parallel path current capacity is 10 amperes. Okay. So this is the per parallel path current capacity per parallel path. Determine the voltage rating. Okay, so I have to determine the voltage rating. So current rating, power rating, all those things, right? One connected as lap winding and wave winding. So let's do it for the first case when it is connected as lap winding. If it is connected as lap winding, so A will be equals to P. So we'll have 4 parallel paths, right? So let me draw, and per turn EMF is there, 10 volt per turn. Total number, so total I have 100 turns. Okay, total I have 100 turns, and I have 4 parallel paths. So in each parallel path, how many turns I will have? 20 turns, right? So turns per path will be 20, right? Per path turns will be 20, right? How? Basically, it is the total number of turns, total turns divided by path. So this will be equals to total turns is 100 divided by path. Path is number of path is 4. So 25 turns per path, right? And each turn has 10 volts. So how many, like, because each, like this is a like equivalent circuit, right? So I will have 4 parallel paths, and this is the whole EMF, right? And each path has 25 turns, right? So what is the EMF induced in 25 turns? I know per turn EMF is 10. So for 25 turns, how much EMF will be there? So E, right? E will be equals to EMF per turn, EMF per turn into turns per path, right? That will give me the value of E. Now again emphasizing that just mugging up formula is not good, right? Understand the concept. That's why, like, I'm writing all this, but will you remember this? No, right? Understand, draw the circuit, understand it. So this will be EMF per turn. EMF per turn is 25 into turns per path. Turns per path is, sorry, EMF per turn is 10 into turns per path is 25. So this will be 250 volts. Okay, so this will be 250 volts. Okay, so this is one of the answer. Okay, now the second answer. The current rating. What will the current rating? So I know each turn maximum can support how much current? 10 amperes, right? Each parallel path can support 10 amperes of current. They told me each per parallel path the current maximum current supported is 10 amperes. So again, this will also will be maximum 10 amperes. This will be maximum 10 amperes. This will be maximum 10 amperes, right? So overall current, armature maximum current rating of the armature, IA will be current per path, current per path into number of path. Okay, so this will be current per path. Current per path is 10 into number of parallel path is 4. So 40 amperes will be the current rating. Now what are they asking also? They are asking the power rating. So what is the power rating? So power rating, right, is simply the voltage rating into the current rating, right? So it is 250 into 40. So this will be 10 kilowatt. This will be the power rating basically. Okay. Let's solve it for the second case, that is the wave winding. So in wave winding, what happens? In wave winding, I will have only two parallel paths, right? A will be 2, that is fixed, right? A will be 2. So A will be 2. Now what is the turns per path? Now turns, again the same thing, right? So again same thing, I'll just copy and paste literally. Just copy and paste this. Same analysis. No, nothing will change, right? Just the turns per path will change. That's why these values will change, except that everything will remain same. Okay. Oh shit. Let me keep it here. Discrete. Okay. So turns per path this time will be, I have two parallel paths. This will be 100 by 2. So this will be 50. Okay. So this is 50. Now this is turns per path. So 10 EMF per turn into turns per path, 10 into 50. So this will be 500. Okay. And current per path into number of parallel paths, this will be 2, right? This will be 2. So this will be 20. So current rating will change, reduce, and voltage rating will increase. But if you see the final power rating, right? Power rating will be unchanged. 500 into 20. So power rating is not changed, but the voltage and current rating changes. Okay, this is a very good observation that you can notice, right? It does not matter whether it is lap winded or wave winded, but the power rating will remain same. The current rating will change. Okay, that is the key takeaway that you should do in this, right? One more thing about rating, I want to discuss one more thing about rating. So in case of DC, right? In case of DC, I can write key, like one thing I want to say. Whenever we are talking about rating of any electrical device, we should always maintain, we should always say in kVA. So I will write here one key point, that whenever we discuss a rating of a device, whenever we discuss about rating of a device, rating of an electrical device, of an device, we discuss as it supplies both active and reactive power, we should mention in kVA. So this is for a generator. I'm discussing this for a generator, right? Because generator is an electrical device, but because at the output I am getting a electrical output, right? So this we are discussing for a generator. except DC generator. Why? Because I told you, right, DC generator gives DC output. As the output is DC, it does not matter, kVA and kilowatt will be same because there will not be any reactive power. So in case of DC generator, my rating will be in kilowatts, it will be in watts, kilowatts or megawatts or gigawatts. So because DC machine only delivers active power because it is DC, simple, it is DC, right? Okay, then I have motor. What about motor? So motor, what is the power output for motor, right? The power output is the shaft power, right? So for motor, basically motor always in the output, it is always driving a mechanical load. So the user does not care whether he is receiving reactive power or not, because he is just driving a load, right? It is a mechanical load. So user cares only about, user cares only about the mechanical load. Okay, user cares only about the mechanical load. So yeah, so as we care about mechanical load means it active power, right? So the output will be in horsepower or kilowatt. So the rating will be in, for a motor, the rating always you will provide the rating in horsepower or kilowatts or watts, whatever you want to say. Okay, so this was about a brief about the rating. And one more thing, one more important portion, that one more key point. What is another key point? Another key point is the rating of a DC machine power rating. Very important to specify, the power rating of a DC machine does not depend on number of parallel paths. Okay, so these are the few things that you should keep in mind, that rating will not depend on the number of parallel paths, but voltage and current rating does depend on it. Okay, does depend on it. So this is very important conclusion that we should take away, right? So one more question is there. This actually I wanted to take in when we were discussing about compound machines, but at that point of time we did not knew what is the number of parallel paths and all those things. So that's why I had to delay this question basically. Okay, so let's solve this question. It is a 4-pole lap wounded machine. So if it is a 4-pole lap wounded DC compound generator, okay, it is a 4-pole lap wounded DC compound generator. Compound generator, have they told us is it a long shunt or short shunt? No. So it is just simply a compound generator. So it should not matter if I assume it to be long shunt or short shunt. So let me assume this only, that here I have the series winding, uh, then the armature resistance, then it is a generator, right? So this will be the back EMF, this will be EG, this will be the shunt winding, So this will be RSH. This will be uh, R series, and what is RSH? RSH they have given me the shunt resistance is 100 ohms, so it is 100 ohms, and the series resistance is 0.02 ohms, so it is 0.02 ohms. Okay, and my armature resistance is 0.004 ohms. Sorry, each turn having resistance this. Okay, this is not the armature resistance. Sorry, armature is made up of 220 turns. Okay, and each turn has a resistance of 100 this much, and it is a 4-pole lap wounded machine. So what is the number of parallel paths? The number of parallel paths is equals to 4 because it is a 4-pole machine. So number of parallel path is 4. So armature is made up of 220 turns. So how many turns are there in each parallel path? So number of turns in each parallel path. Turns per path. It will be 220 total number of turns divided by the number of parallel paths, that is 4. So this will be 55. Okay, 55 turns per path. Okay, now uh, there are 55 turns in a single path, and each turn has this many resistance. So what will be the total resistance of a single path? So resistance per path. So that's why I have told you not to mug up the formula. Okay, not to mug up the formula. So resistance per path, resistance per path, per path equals to each turn has 0.004 ohms, and total how many turns I have? 55, right? Because all of them will be in series, simply they will be simply added, right? So 55 into 0.004, if I just quickly calculate this value, just hold on, 0.004 into 55, 22, 0.22, okay, 0.22 ohms. 0.22 ohms. Okay, now uh, now each path has 0.22 ohms. Now I have 4 of these paths, so 4 of those paths are in parallel, so I have to divide that by 4 again, right? So armature resistance will be what? Armature resistance, armature resistance, because I have like this is the resistance of each turn, right? I have 4 paths, and each path has resistance this whatever we have calculated, 0.22, right? This 0.22, and I have 4 of these paths, so overall armature resistance will be Ra, it will be 0. 0.22 divided by 4 simply. Okay, so this value will come out, same value will come out only, I mean divided by 4, so this will be 0.055. 0.055. Okay, ohms. 0.055 ohms. Okay, this is the armature resistance. Okay, finally after all this hard work we have found out the armature resistance. What we have to find out actually, I don't even know. Okay, if the generator operates at 900 rpm and delivers a current of 50, find out the output power. So flux per pole, I know the flux per pole phi is 0.07 Webers, right? 0.07 Webers. Okay, so I know the speed, I know the flux per pole. I know the total number of conductors. Do I know the total number of conductors? Yes, I know, because I know the total number of turns. So what will be the Z? Z will be, each turn has two conductors, right? So Z will be what? Z will be 2 times the number of turns. So 2 times 220. So it will be 440. Total number of conductors is 440. So I know everything, right? So simply what I can do, I can use the formula of induced EMF. It will be phi Z NP by 60A. Correct? So phi is 0.07, Z is 440, N, that is the revolutions per minute, is 900 rpm, right? 900 rpm, 900 rpm. Poles P is 4, okay, and number of parallel path is also 4, so that will simply get cancelled. So if I just calculate the values, this will be 900 into 440 into 0.07 divided by 60, so 462 volts. Okay, this will be the induced voltage, EG. They are asking me the output power. Remember, what is the output power? So output, right, there will be bit of drops here. In the output there will be bit of drops. Okay, keep in mind that. One more thing, it does not matter whether it is like series or parallel, because anyways this drop will always, okay, it actually does matter kind of. Here they have not told us long shunt or short shunt, so I will assume it to be short shunt, although the answer will not vary much. Okay, it delivers a armature current of 50 amperes. So if it delivers 50 amperes, right, I have to calculate the terminal voltage, right? So what will be the V? V will be EG plus IA into RA plus RAC. Okay, so this will be equals to EG is EG, just hold on, EG will be 462. IA, they have told me that it is delivering 50 amperes. 50. RA we have just calculated 0.055 plus RAC, series resistance, they have already told me 0.02, right? So from here 0.055 plus 0.02 into 50 plus 462, this will be 465.75. okay, this will be the yeah, okay, sorry, what am I doing, how am I adding it? I have also forgotten the key will key seal. This will be negative, right? Sorry about this. So minus, okay, 3.75 into 2, so 458.25. I'm sorry, I'm also like, it is delivering, right? So drop will be like this, correct? What am I doing? I'm also in some other mind. So V will be this will be negative, so it will be 458.25 volts. Okay, what about the current? So I, right, will be combination of these two currents, right? Because bit of current will go into the load, but some current will go into the shunt, right, as well, right? So what is IA is a combination of the load current plus the shunt current. So what is the shunt current? Shunt current, ISH, will be equals to the V upon the RSH. So V is 458.25 divided by shunt resistance. Shunt resistance is 100 ohms. So this will be 458 divided by 100, 4.525 amperes. Okay, so from here I can directly calculate the load current. So load current will be this plus armature minus armature current. Armature current is 50, so load current will be 45.4175. 45 0.4175 amperes. So basically my power, right, output power rating will be V into IL. So this 45 point this into 458.25, so this will be 20.813 kilowatts, right? This will be the answer. The power rating of the compound generator will be 20.813 kilowatts. Okay, so yeah, that was about like the questions. So these are the summary whatever we had discussed about the power rating, current rating, all those things, right? Okay, so let's now solve few questions. So we have a 6-pole lap wound DC generator has 240. It's not even, again it is a lap wound DC generator, right? So first of all it is a lap wound DC generator. So number of poles will be equal to number of parallel paths, 6 poles, so it will be 6, and it is a generator. They have not mentioned whether it is a shunt series, I don't care, with 240 coils. So 240 coils and 2 turns per coil, 2 turns per coil, right? The resistance of each turn or turn is 0.03 ohms. The armature has a length of 50 centimeter. Okay, okay, armature length also is given 50 centimeter and radius of 20 centimeter. So armature, right, is in cylindrical shape. Armature is in cylindrical shape, correct? Okay, so the length they have given me of the armature, length they have given me, length is equals to 50 centimeter and resistance, sorry, not resistance, the radius is 20 centimeter. Okay, the air gap flux density is uniformly distributed over 0.6 Tesla over the pole shoe. So it is uniformly distributed. So they are telling me that the flux density is constant, 0.6 Tesla. It is constant, assumed to be constant under the pole shoe. Okay, so I will under the pole shoe, constant under pole shoe. Each pole covers 40 degree of the armature periphery in mechanical angles. So each pole, right, will cover 40 degrees. So I have a pole here, and under the pole shoe the armature, sorry, the flux is constant, the flux density is constant, and each pole covers 40 degrees mechanical. Okay, if the armature rotates at 1200 rpm, determine the no load generated EMF. So N they have given me, N is 1200 rpm. Remember whatever formula we had derived, right, phi Zn P by 60A, okay, that was for a sinusoidal, right? Here is the flux density sinusoidal, no. If you see the flux density, if you want to see the flux density, it is not sinusoidal. It is not sinusoidal. So it is constant under the pole shoe, right? So for, let's say, for certain region it is constant, then again the pole shoe is going away, north pole is going away, then again we are in south pole, right? So it is just like this. Here I will have a pole, correct? My drawing is really bad. So here I will have a pole, so my armature conductor will be here. So in this whole region the flux will be constant. Again, once my armature conductor is here, no pole is there, so flux will be 0. Again, once I reach here, the flux will be there for 40-degree mechanical, right? Now this is a electrical waveform, right? This is not a mechanical waveform, right? So this is electrical, omega here is electrical. So if it is 40-degree mechanical, what is electrical? So theta electrical will be p by 2 into theta mechanical, correct? Okay, so it will be p by 2. P is 4. P is, sorry, how many poles I have? 6 pole, right? This 6. P is 6 divided by 2 into theta mechanical, that is 40. So it will be 3 into 40, that is 120 degrees. So this will be 120 degrees, right? One pole will be 120 degrees, right? Okay, so now what do we need to find out? So our equation, right? Equation of induced EMF. What will be the equation of induced EMF? I know there are total 240 coils, okay, and there are 2 turns per coil. Now what is the induced EMF per coil, per path? So total 240 coils are there and I have 6 parallel paths, right? So 40 coils, so coils per path is equals to 240 divided by the number of parallel paths, that is 6. So it will be 40. Okay, 40 coils per path. Okay, what is the overall induced EMF? It will be a one coil, what is the, whatever is the induced EMF in one coil multiplied by 40, right? Because I have 40 coils in a path. So per coil induced EMF, what will be the per coil induced EMF? Again, E coil will be what? So one doubt you might have is, sir, if the flux density is constant, how is their voltage getting induced? Because I know that voltage equals to NC into d phi over dt, right? And you are saying, sir, flux density is constant, so this would be 0, right? Is it so? No, it is not, because this is flux linkage, right? But my flux density is constant, but I have not told you that my flux linkage is constant. I have not told you about that, right? So here I can say that basically if I have a small circular region, right? Again, this radius is r. So what is, like, this length, let's assume this length as L, because the whole pole will be facing this, right? Whole pole will be facing this. So whatever flux density is coming, it will come here, right? So what I'm getting at is, I know my formula of flux. What is flux? Flux is equals to flux density into area, correct? So if this is a circle, then what is this small, if I assume a small angle here, let's say alpha, what will be this, or let me write this as delta, what will be this length? This will be r d delta, right? Very basic thing, right? If this is small angle delta, what will be this length? R d delta. And what is the total area that the pole will cover? This whole axial length, right? So area that the pole will cover will L into R delta, right? So small area, small change in area dA is L into R delta. Okay, so that is what I am trying to get at, because the area will constantly keep on changing, and if you have studied EMFT, you'll know if the area also changes, then also there can be induced EMF. Then also there can be induced EMF. So that is the key point to note here, right? Area will change. So basically, E coil will be NC into, I am talking about the instantaneous value. E coil instantaneous, right? Instantaneous, E coil instantaneous will be NC into, that is d of dt into b value is constant always, into, otherwise it is 0, right? Else either it is 0 or it is some constant value, into the small area dA, right? Or not dA, sorry, area. So small area dA is this, okay, yeah, basically here my flux density is constant, so this will be NC into b will be outside, this will be dA divided by dt. Okay, that is what my E coil is equals to, E coil of t. Now what will be the average, E average? Because of course before commutation this will be downwards, but after commutation this will go up top, right? This will go top. After commutation the induced voltage expression will be something, I mean it will be it will be commutated basically. So after every 180 degrees this will be positive. So my induced voltage E waveform, induced voltage E will, E of t will be periodic for every pi, electrical, right? 180, because we are doing commutation, so the negative half cycle becomes positive only due to commutation, okay. So I can write, I can take this dt on the left hand side, this will be E coil of t into NC into B into dA into dt, right? Now what is the E average, E coil average? E coil average, E coil average will be what? Integration of every pi, because it is a periodic over every pi, and it is like I have commutated it, it is positive, so it will be 0 to pi into E of coil into t dt, correct? Divide by pi, okay. Trust me, no one, first of all, no one will take this question, and even if anyone takes in this whole gate industry, right, if anyone takes this question in this whole gate industry, they will try to just write the formula, mug things up. I am deriving, this is how I will solve in the gate examination. So this is a totally new question, trust me, this is like this, you will not see anyone else solve. Even if someone else will solve this, they will just try to use the formula, they will not explain you the concept, okay. I am explaining you the concept, trust me, whatever you're learning, right, this is the best content that you're learning. So it is E coil average of this, right? So basically I know what is this E coil into dt, this is this, right? So basically it is NC dB into dA, okay. And one thing I know, that the angle, right, I am rotating angle from, let's say, 0 degree to 180, but I know that my flux density is 0 for, let's say, like it is symmetrical, right? It is symmetrical after every 180. So basically this will be 30 and this will be also 30, correct? Because out of 180 I am covering 120, so 60 is left, so 30 will be covered on the left hand side, 30 will be covered on the right hand side. So this is 30 degree, this is 30 degree, right? Okay, so 30, okay, and this is 120, okay. So what I can say is that 30, 120. So what I can say, for this 0 to 30, right, I'm integrating for this whole 0 to 180, but for 0 to 30 and for 150 to 180 it is always 0. The induced voltage also will be 0, because the flux density itself is 0, right? If there is no flux density, because it is a product of flux density and area, if the flux density itself is 0, induced voltage also will be 0. So here I can actually write my limit will be 1 by pi. This limit will be from whatever angle degree this is, it is 30 degrees to 150 degrees, right? So this will be 30 degrees to 150 degrees of this value, right? NC into B. So B is constant value, otherwise it is 0, but in that range, right? In from this is what? This is 30 and this is 150 degree. Okay, so 30 to 150, right? So between 30 to 150 the value is constant. What is the value? The value is 0.6, right? 0.6, yeah, the value is 0.6. The value is 0.6 Tesla. Okay, so NC is how much? So this is, remember, this is EMF per coil. So but do I know how many coils are there in series? Total number of coils is this. I know, I have already calculated the, what is it, coils per path is 40 coils, right? So 40 coils per path. So overall, right, whatever value I will calculate, the overall induced EMF E will be 40 into induced EMF per coil average, right? Keep this in mind. So my EC average will be this value. So this will be 30 to 150 degrees, and NC per coil turns, it is 2 turns per coil. 2 turns. NC is 2. NC is 2, right? Turns per coil. So this will be 2 into B, that is 0.6 into R D delta, right? So R is how much? 20 centimeter. R D delta. Also L is there, right? L also I have to multiply. Length also I have to multiply, right? L into R D delta, right? So L is how much? L length, I had 40 centimeter, I guess. It is 50 centimeter, 50 and 20. So 50 into 20 into D delta. Okay, divide by 1000, correct? This is 1 only, right? This is 1 only. Okay, so this is 1 only. This will be 2 into 0.6. So 2 into 0.6 is 1.2 into D delta. Okay, remember this is in radians. This also should be in radians only. So this will be basically 1 by pi. So 1 by pi into 1.2. This also has to be in radians only. So what is 150 in radians? So 150 in radians. So 30 in radians is pi by 30 in radians. Basically 30 in radians. How much is 30? Pi by 6, right? Yeah, pi by 6. So it is 5 pi by 6. 5 pi by 6 minus pi by 6. So this will be 1 by pi into 6 by 5 into 2 by 3 pi. Okay, 2 by 3 pi. So here 3 will get cancelled. This will be 2. So 4 by 5. 4 by 5. 4 by 5 volts. Okay, but this is the induced EMF per, what do you call, per turn, per coil. Induced EMF per coil. Okay, one very small mistake I had made. I am integrating here with respect to some radians, but this is function of time, right? So I have made a very small mistake. So this is omega t, not t, right? But here I have t. So I'm integrating with respect to t. How will I convert this then? So like omega t is varying. So I will write here one very small mistake, right? This is wrong. This thing is wrong. The limits are wrong, right? Limits are wrong. So I know I am varying my omega t. Like I will not write 0 and I will not write 0 or whatever the values, right? 0 to pi, right? I'm varying my omega t from 0 to pi. So how will my t vary? So t will vary from T will vary from 0 by omega to pi by omega. This is where I messed up, right? This is where I messed up. So this omega is in electricals, remember? This omega is in electricals. Okay. Yes, omega is in electricals, yes. Okay, that is what I messed up actually. Now I don't know this omega frequency actually. I don't know this omega frequency. Okay, I know mechanical frequency, speed, right? So this is omega electrical. I know omega m. Omega m is given to me. Omega m is 2 pi n, the rotation of the armature divided by 60. Correct? Because this thing is known to me. I don't know the frequency here. So I will convert this. And my what is my omega e? Then so what is my omega e? Omega e is equals to p by 2 omega n. So I will replace this. I will use this substitution. Okay. So this is where I messed up actually. So here, right, instead of this 1 by pi and this is wrong actually. This is wrong. The limit should be, I will write the proper limits here actually. Yeah, I will write the proper limits here. This will be pi by omega and this, right, 30, yes. Basically, right, this should have been pi by omega e, that's it. This is fine, these limits are also wrong, but here if I am varying from, like, actually what should be the limits, I will tell you what should be the limits. The limit should be 0 by omega e, that is 0, to pi by omega e of e of t dt divided by what? Upper limit minus lower limit. So pi by omega e equals to, now this is in time domain, right? Not radians, this is in time domain, but the right hand side is in angles. So for time period, this to this angle is from this to this. I mean for time 0 to pi by omega e, omega t is varying from 0 to omega. Sorry. So for time 0 to pi by omega e, omega t is varying from 0 to pi, right? So the right hand side, as the limit, as the differential is angular, so right hand side limits are correct, but the left hand side limits were wrong. So this is correct. Okay. So I just missed a extra omega here. This should have been 1 by omega e by pi. Okay, that is what I messed up here, right? So the right hand side value, whatever I have calculated, is correct, 4 by 5. Okay, this is correct, right? That's why this question is very difficult, and this can be asked one day if they want to frame a very difficult question. So 4 by 5. Okay, and here, right, what will happen? Now I can directly compute the average. So this value is the basically average, right? EC average. So actually, instead of it dividing by 1 by pi, I have to divide by extra 1 omega e by pi, right? That is what I messed up. So this into omega e also will be there. Okay, that is where I messed up. Omega e also will be there. Why omega e will be there? Because this quantity, e coil of dt, is this quantity, right? But I'm integrating this, so limits are also fine. If I'm integrating from 0 to pi by omega e, then the right hand side limits will be from 0 to pi. That is fine, because right hand side is with respect to angle, left hand side is with respect to time. But once I'm dividing here by 1 by pi by omega e, this value I'm dividing, so right hand side also I should divide by the same value. Previously I divided by pi, so but I have to divide by the same value, pi by omega e. Okay, so this will be omega e into 4 by 5. So omega is how much? We don't know. I don't know what is omega e. I know what is omega m. So omega e is p by 2 into omega m. What is omega m? Omega m is 2 pi n into 60 by 60. N is what? It is rotating at 1200 rpm, right? It is rotating at 1200 rpm. So this will be 1200 divided by 60 into 4 by 5, and p is basically 6, correct? So now everything is perfect. This is the only the coil average voltage, right? Only the coil average voltage. I have yet to write the overall average voltage, right? Okay, so coil average voltage I will write down. So this will be 3 into 2 into pi into 1200 divided by 60 into 4 divided by 5. So 300 and 301.6 volts. Okay, and what is the basically coils per path? It is the coils per path, that is what I'm trying to calculate. Something I'm messing up here. 2 pi n by 60. Okay. Okay, one thing I messed up here, right? Okay, one thing. This is not divided by 1000. Okay, another mess up I have made. So this is a big question, right? That's why I'm messing up all this. This is not divided by 1000, right? It should be divided by 10,000 because 1 centimeter is 10 raised to the power minus 2 meter. Okay, sorry. This will be divided by 10,000. So here I will have another extra zero messed up here by 10. Everywhere I will have a divide by 10. Okay, so here also we'll have a divide by 10. So this will be divided by 10. This also will be divided by 10. So this will be 30.16. Okay, that is what I messed up. 30.16. Yeah, one more small mistake I had made. So like I want you to learn from the mistakes, right? Whatever mistakes I am making, you also, I want you to see it as well, so that you also don't make this kind of mistake. So whenever I tell you, right, d delta, what does it mean? This d delta is a physical value, right? Because I'm rotating by delta angle. I'm rotating the armature by delta angle, right? I'm rotating the armature by delta angle. So in the time domain, if I'm going from 0 to, that is my mistake, if I'm going from 0 to pi by omega, so omega t electrical will go from 0 to pi. But what about omega mechanical? Omega t mechanical, right? Because this is the angle that is the unit of delta. Okay, because delta is a physical quantity, it is not an electrical quantity. Delta is a mechanical physical quantity, right? Delta is a physical quantity. I'm rotating here, it is a physical value, right? Actual value, it is not an electrical quantity. So that's why another mistake I had made, that I have to write the limits of omega m into t, not the omega t, right? Because here the left hand side is fine because it is with respect to dt is the unit of time. So here the limits are with respect to time. But on the right hand side, if I see on the right hand side, the units are with respect to delta, and delta is a mechanical unit. So I have to write the mechanical. So that was my mistake, sorry. So if omega e into t is going from 0 to pi, what will omega m into t go? So I know this relation, omega e is equals to p by 2 omega m. So I can replace here omega e with omega m. So this will be replaced basically p by 2 omega m into t will vary from 0 to pi. So omega m into t will vary from 0 multiplied by anything is 0 only, to pi into 2 by p. That is one mistake, again another mistake that I have made. So this values will change. Basically 2 by p is 1 by 3. So a 1 by 3 will be multiplied here, right? Extra 1 by 3 will be multiplied. That was my mistake. I am sorry. I am really sorry. So here this 1 by 3 will be there. Okay, extra 1 by 3 will be there. Okay, because it is a mechanical quantity, it is not an electrical quantity. That angle is a mechanical quantity. So this 1 by 3 will be there. Okay, so I'm really sorry again. So this will be 1 by 3 again. This also will be 1 by 3. Okay, let's do one thing. Let me calculate everything afresh, or like there will be huge confusion. I don't want the confusion to build so much, right? So what I will do, let me just do one thing. Let me delete these things first, not delete. So here, right, the limits will be changed, correct? So if limits are changed here, this will not be 150, this will be 150 divided by 2 by p, right? So 150 divided by 3 to 30 divided by 3, correct? So that's why the 1 by 3 has came up here. So I have just converted it into radians. So this value is 1 by pi into 1.2 divided by 10 into pi. So ultimately this value is what? If I just want to calculate, this will be 4 by 6 into 1.2 divided by 10 and divide by okay, just hold on, 4 by 6, right? Am I correct here? Yes, 4 by pi. Just hold on, I'll just quickly calculate this instead of all this mess up, right? I will mess up something. Okay. Oh, sorry. Here was pi by omega was also here. So let me do it afresh. Let me do it afresh. Let me do it afresh. Okay, that will be the best thing. Okay, so this will be pi by omega e, and this will be 0 by omega e, because the left hand side is in units of omega e, sorry, time. So this will be pi by 1/2 cycle will be then 1 by 1/2 cycle will be pi by omega e seconds. So this value will be integration. On the right hand side it will be 1 by pi by omega e only. I will replace omega e later on. Integration. Now as I'm moving from 0 by omega e to pi by omega e, that means I am going from for the angle case, because for 0 degree it is 0 only. I will start from 30 degree, 30 degree, right? So 30 degree electrical, but what about mechanical? Mechanical will be 30 divided by 3. So if I want to convert this into radians, so pi by 6 divide by 3, right? Here it will be 5 pi by 6 divide by 3 into this value 1.2 divided by 10 into d delta. Okay, so let me write it neat and clean. So this will be omega e divided by pi into 1.2, so 12 by 100 into 1 by 3. I can take common. This will be 5 pi by 1 by 3 into 6. I can also take common. This will be 5 pi minus pi. So this will be 4 pi. Correct? So here pi will get cancelled. So this will be 6 into 2. So 8 pi omega e. This 6 will cancel this 2, 2, 8, 8 by 100, or 8 by 100, or 8 by 300. Okay, or this can be written as 4. If I multiply, yeah, 4 can be multiplied here, 25. So this is 2 upon 75 omega e. Okay, now this is the a single coil average, right? Now if I want to further write this, what is omega e is equals to? Omega e is equals to p by 2 omega m. So this value is equals to p by 2 is 3 into omega n. Omega n is 2 pi n by 60. So 2 pi n, that is 1200 by 60. So this value is like, this is 20. So 20 into 2 into 20 into 2 into 3. So 120 pi. So this comes out to be 120 pi. So this will be basically 120 pi into 2 by 75. So this comes out to be 10 point something, 10.05 volts. Correct? Okay. So this will be my EC average. Now I will write down what is the overall induced voltage. Overall induced voltage will be the number of overall coils in series into the number of coils per path into the per coil induced EMF, that is 10 volts, and number of coils per path is 40, right? Because it was 240 number of coils divided by the number of parallel paths 6. Yes, so this will be 40 into 10.05. So this comes out to be 400 something, right? 40 into 10.05 comes out to be 402 volts. So this is the no load voltage answer. Okay, now second case is the case in which there is load connected, right? If there is load connected of, what they are telling me, there is load connected of 40 amperes. So for that I need to find out the armature resistance. So to find out the terminal resistance, they are asking us the terminal voltage, not the resistance. For that I will need to find out the armature resistance. They have told the resistance each turn is 0.02 turn, 0.0203 ohms. So resistance per turn is 0.03. So how many turns I have in series? So in series I have 40 coils, right? And each coil has 2 turns. So it is 2 into 0.003, that is resistance per coil in a single path, into 40, because I have 40 coils in a path, divided by the number of parallel paths, because they are in parallel, divided by the 6. right, because all these are in parallel. So that's why this will be division. So I'm not explaining you the formula here, I am just directly writing it. So this will be 40 into 2 into 0.03 divided by 6. So 0.4 will be the armature resistance. Okay, 0.4 ohms will be the armature resistance. Now I have to find out the terminal voltage. Terminal voltage for a generator will be Eg minus Ia Ra. Okay, so Eg is 402 minus Ia Ra. So Ia they have told me that it is supplying how much current? 40 amperes of current. It is supplying 40 amperes of current. So 402 minus 40 into 0.4, that is minus 16, right? Minus 16. So 16, so it will be 386 volts. So I have not used any formulas, I have just solved using basics. So I want you to also solve using basics. I made mistakes, so I want you to see those mistakes and learn from those, right? Always know what kind of angles you have to put, what are the things that you have to do, right? Just be careful about the mistakes. So now let's move on to the next topic, that is removal of brushes. So if I remove a brush, what will happen? In lap winding, multiple positive terminals and negative terminals exist, okay, corresponding to multiple parallel paths. So when one brush is removed, the two parallel paths are disconnected and they become in series. So we will see the effect. However, in wave winding, there are only two brushes, one positive and one negative, because A is 2, thus brushes cannot be removed, right? So in lap winding, there is provision to remove brushes, but in wave winding, of course, if you remove the brush, machine will not work, commutation will not work. But like, even though we don't want to remove brushes, but just in case, if we had to remove brushes, we should know what will happen to the current and voltage ratings, right? So let's take example, if I remove this brush for a lap winding, right? This is a lap winding. So number of brushes is equals to the number of parallel paths. So if I remove a single brush, right, what will happen? So basically these will be like, this whole path will be simply short circuited, right? This will provide what? Overall this is providing zero voltage, no voltage at all, right? This path is providing no voltage, correct? So these two paths are simply short circuited. So no current will flow through here. Basically this path will be there, 4 ampere current will flow through here, and this path will not be there. So 4 ampere current will flow through here, and for the rest of the 4 ampere current will come through here, okay? And will this path work? Okay, this path will be functioning, right? This path will be functioning. Yeah, these path will not be functioning. So this can provide 4 amperes here, this can provide 4 amperes here. Yeah, these two paths will be functioning, okay, but these two paths will totally be out of order. So we will see what will happen basically, okay? So ultimately, right, through here current will be 0 because induced EMF is 0, right? Overall this is short circuit, this whole path is short circuit, right? This V is 0, so current through this coil also will be 0 amperes, through this coil also will be 0 amperes. Only 4 amperes current will flow from here and 4 amperes current will flow from here, right? So ultimately, previously I was able to give 16 amperes, now I will be able to give only 8 amperes because 4 amperes will come from here, 4 amperes will come from here, and overall 8 amperes will come. Previously 16 amperes was coming, if you remember it, okay? So now let's understand more in depth why the current will be 0 if the voltage is 0. So we'll understand this with a question. So this is the first question that we will solve. So we have a 6-pole lap wound machine, right? So if it is a 6-pole lap wound machine, that means how many brushes I will have? For a lap wound machine, the number of brushes is 6. Number of brush is 6, okay? Has a developed power P watts. P watts is the developed power, that is at the output I am getting P watts, and a brush voltage of E. Brush voltage of E means basically the output voltage is E and the power is P, right? Armature current, let's say, is Ia, overall output current including all the parallel paths. So my P will be equals to E into Ia. I'll show you in the diagram as well, okay? So this is the case 1 where I have 6 brushes. So 6 brushes I will have, so 6 series coils I will have, 6 parallel paths, and all of these parallel paths output will be E voltage, brush voltage will be E, and the current will be Ia, right? So what will be the current through each of the coils, that I want to know, okay? So this potential is E, power here is Power in the case 1 is E into Ia. Now what is the current here? Remember here there are three paths, 1, 2, and there should be three paths plus, okay, yeah, 1, 2 and 3. Three paths are there, right? So this will be divided Ia by 3. So this will be Ia by 3, this will be Ia by 3, this will be Ia by 3. Okay. Now what is the, like here there again there are two paths, right? Ia by 3 is coming out, but here again there are two paths. Again for a lap winding, remember the signs will alternate, right? That's why, what is lap winding? The ending of one of the coil is connected with the starting of the other coil. So starting will be plus, ending will be minus. That's why if you see signs alternate here, signs are alternating here. Okay, I hope you understood this point. So signs will alternate here. So this will be Ia by 3, Ia by 3, Ia by 3. Okay. Now, so this will be what? Ia by 6, right? This current will be Ia by 6. This current will be Ia by 6. So is this something familiar? Yes, right? Basically, coil current, right? IC, I coil, maximum coil current will be the armature current divided by the number of parallel paths. That is what we learn about lap winding, right? Number of coil current will be armature current divided by the number of parallel paths, that is Ia by A. In this case, A is 6, so it will be Ia by 6. Okay. So this is the case 1. Now in the case 2, they are telling me that the 3 adjacent brushes are removed. Any 3 adjacent brushes you remove, won't matter, but I will do it for only single case. For other case as well, you can derive it. So case 2, if the 3 adjacent brushes are removed, okay. So if the 3 adjacent brushes are removed, let us remove these 3 adjacent brushes. Okay, so let us remove these 3 adjacent brushes. If I remove these 3 adjacent brushes, then what will happen? And let me short circuit this path. Then these coils will be short circuited, correct? These coils will be short circuited simply. Okay, so if these are short circuited and if the brushes are removed, what will be the current through here? That is the important portion to understand. So remember, what is the induced EMF here? Let me write the induced EMF to be EC. Okay, if the induced EMF is EC, what is the current? If the coil resistance is RC, the rated current will be IA or IC will be equals to EC divided by RA. So each coil RC, EC divided by RC, each coil, which is equals to IA by 6, right? Okay, so induced EMF divided by RC. So here all the coils will induce their EMF, but brushes are not there, right? So they are simply short circuited, right? Because inside the machine, in lap winding, the positive terminal is connected with the negative terminal, that is there, but brush was there, due to which current was flowing out, but brush has been removed. So these paths have been open circuited now, right? Only the coils connections are there. So now the interesting fact, voltage will still be induced, right? So what is the voltage induced in this whole loop? So this is one of the loop, right? This is one of the loop. What is the overall voltage induced? If I apply KVL here, I see that this will be plus minus EC. This will be minus plus EC, right? This was positive here. This was minus plus EC. If you remember, this was minus plus EC. So this and this voltage will get cancelled out. This voltage and this voltage also will get cancelled out basically, because I am removing 3 brushes. Yeah. So this coil voltage, will get cancelled out. Plus minus plus cancel out. Plus minus plus cancel out. So overall here, right, the voltage here is 0. Voltage here is 0. Okay. So if the voltage is 0, what will be the current? So it's just like a circuit that I have resistance here or coil, anything you want to write. I have like this is RC, 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 RC. So I have 4 RC, right? RC, 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 RC. So here I have 4 RC and the induced voltage is 0. So what will be the current? Current also will be 0, right? No current will flow through here. So here 0 amperes of current. Voltage, induced voltage is 0, as voltage, current is equals to voltage by resistance. Current is also 0 in this case. Okay, voltages are getting induced, but no current is flowing because these voltages are opposite to each other, right? That's why they are cancelling each other out. So here again there is some voltage. What is the voltage induced? EC. EC voltage will still be induced. Divided by RC. So here, through here the current will still be there. What is the current through here? IA by 6. So through here the current will be 0. Here current will be there, IA by 6. Okay, and here also IA by 6 current will be there. So ultimately from here IA by 6 current will be there. IA by 6 current will be there. From here actually no current will flow. This is open circuited, right? No current will flow. And from here as well IA by 6 current will come out. Okay, so from here IA by 3 current will come. So what will be the power rating now? So power rating, E voltage will still be there because E is simply EC. E is simply EC because it is one coil voltage, right? Or is it? So this is connected here. This point is connected. This negative terminal is connected. Negative terminal. Okay, negative terminal is connected here. Yes. Yeah. E will be still equals to EC. In the previous case as well. Previously, if you see, the terminal voltage was equals to EC only. So this will not change. So this is EC into IA. But now the voltage does not change, but the current changes. Current is IA by 3. Previously it was IA by 6. So the power rating will be what? P dash. P dash will be P by 3. So power rating will be 1/3 now. So in the options, the terminal voltage will still be E. The power rating will be 1/3. So option D will be correct. So let us take more cases. So this was the most of the toughest case. Now let me take more cases, right? So if, let me go through it over again, that if one of the brush is removed, what will happen? Again same thing, right? If each of them has, let's say, coil resistance of RC, RC, RC. So what happens? All these are in series. So all these will be in series. Okay, these 4 coils will be in series. So, and what is the induced voltage overall? I see these voltage and these voltage are cancelling each other out. So voltage in series are added. So voltage is 0 and this is RC, 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 RC. So what will be the current here? In this case, this I, let me name IX. IX will be simply V by 4 RC, which is 0 because voltage is 0, right? So current through here will be 0. So no current will be flowing through here, right? No current is flowing through here. All of the current will flow through here and here. So if previously there were 4 parallel paths, right? 4 brushes are there, 4 parallel paths. So it was IA by 4, IA by 4. But only 2 parallel paths will work now. So this will be IA by 2 and IA by 2. Okay. So overall current will come IA by 2. This will be plus minus, yeah. So IA by 2 current will come here. So this brush is removed, right? So this connection is gone actually. No current will flow through here. And IA by 2 current will come from here. So overall, sorry, not IA by 2, sorry, IA by 4 current will come from here because this path is neglected. So IA by 4, right? Sorry, not IA by 2, IA by 4. This will be IA by 4. This will be IA by 4. So this current will be IA by 2, right? So basically previously it was E into IA. Now current has become IA by 2. Same thing is written over here. So current has written to IA by 2. So power capability, voltage will be same. Voltage will be E only, but the power will be reduced because it is E into IA dash. So it will be P by 2 basically. E into IA by 2. So it will be P dash will be P by 2. So power capability will be halved, current capability will be halved. What about if I remove 2 adjacent brushes? If I remove 2 adjacent brushes, then what will happen? Same thing, if I remove 2 adjacent brushes, right, this connection will not be there, this connection also will not be there, okay, because brush has been removed. So ultimately coils will be short circuited, right? Now there will be circulating currents flowing, there will be a bit of imbalance. Why there will be imbalance? There will be imbalance because what is the, now these, all these are in series, right? All these are in series. Okay, all these are in series. So what is the current? What is the current? So let me write again RC, RC, RC. So let me write that overall this, let's assume that this overall resistance is RC, right? Two coils resistance is R coil. So resistance between two brushes is R coil, RC. So what is the voltage here? So let me not just write 4 volts here. 4 volts will be bad actually. Let me, okay, let me just take one coil. Otherwise you will get confused. Okay, because there are two coils, there is a bit of chance of confusion, right? So let me not write here values, else you will get confused. So let me remove this. Let me make this a single coil only. I'll do it. So okay, let me keep the plus sign here, let me keep the minus sign here. Yeah, let me keep the plus minus sign, this will be plus minus, and this will be plus minus. Okay, let me assume this to be single coil only, so all these are single coils only. So it is like a single coil only. Okay, just ignore it. Okay, ignore by drawing, it is single coil because I want to mention one thing. So this right here also I will delete these things, otherwise you will get confused. So let me delete these things, this, and it's a single coil, right? I just wanted to conclude on one thing, so I will conclude that. So yeah, this will be this. Okay, just ignore my drawing because this lecture is already super long. Okay, I'm sorry for the super long lecture, but the concepts are more important, right? So yeah, so each coil has resistance RC. Now what is the overall induced EMF? So what is the each coil induced voltage? EC, let me assume it as EC. So this is EC, right? So this, what is the voltage? This is EC. So this is plus EC, this is minus EC, this is cancelling out, but this is still plus EC, right? So overall voltage is plus EC, right? Overall V, right? KVL in this loop is plus EC, and resistance is how much? 3 RC, right? R is 3 RC, correct? R is 3 RC. So overall current, right? Current will be what? Current will be EC by 3 RC, right? What is EC by RC? So EC by RC, this is not 8 volt, sorry, it's not 8 volt. This is simply EC or E, right? So EC by RC, if you remember that if all of the parallel paths were working totally perfectly, EC by RC is IA by 4, right? Because overall current divided by the number of parallel paths, that is 4 in this case, so IA by 4. So EC by RC, I know this value, that EC by RC is IA by 4, right? For every coil, it is rated for IA by 4 amount of current, but it is EC by 3 RC, so there is bit of imbalance of current, right? So that is the problem. So this is carrying IA by 12 amperes of current. So this coil will give out here, the current will leave from the positive terminal, so current will leave from here only. So current will be IA by, okay, this is also open, right? So current will basically leave from here, okay? So current will leave that, this, what is the value of current? IA by 12. Okay, am I correct? Yeah, IA by 4 was EC by RC. EC by 3 RC will be IA by 12. So EC by 3 RC will be IA by 12. So IA by 12 is coming from here. How much? This is again, this voltage is rated and this coil is totally fine, no problem with this coil. So it is, what is the current here? EC by RC. This resistance is RC, right? So here IA by 4 current will flow from here, IA by 4 current will flow. So from here IA by 12 current is flowing, from here IA by 4 current is flowing. So from here how much current will flow? From here how much current will flow? So from here IA by 4 plus IA by 12. Okay, so this will be 3 Ia by 12 plus Ia by 4. So Ia by 3 current will flow from here. Okay, so actually you have to calculate, you cannot directly blatantly say that what will happen to the rating and all those things, right? So now you can see Ia by 3 current is flowing. So what is our power rating now? P dash, it is E into Ia dash. So E is EC basically, that will not change. Ia dash is Ia by 3 now. So power rating has reduced by 1/3. Okay, so that's why it is written that if I remove two adjacent brushes or more than two brushes, maybe it might happen that the circuit may break for specific paths and causing circulating current. So this is the Ia by 12 current, and like imbalance of current is flowing. So from here Ia current is flowing, from here Ia by 12 current is flowing. So bit of imbalance is there that can damage the circuit. So we don't want to remove the brushes, but even if we do remove the brushes, still the circuit can work. Okay, that is the conclusion. So I want to leave this one as homework, that there are two DC machines. You try these questions by yourself, and in the next lecture I will solve this question. Whatever knowledge we have gained in this lecture, you try it, and I will solve this question in the next lecture. I hope you have enjoyed this. Trust me, this lecture, right, you will not be able to find these kind of quality content, explanation, theory, question solving nowhere. Trust me, like the droppers who have studied from somewhere else, right, they will know this, right? They will know what kind of quality you guys are getting. Trust me, you just search anywhere in the internet, any paid course you search, this lecture, this content you will not find anywhere else. Just believe me on that. Okay, so yeah, I hope you have enjoyed this lecture. I will see you in the next lecture. Until then, happy learning, and make sure to like in this video, make sure to comment on the first video of the playlist. That will really help us out. Thank you, and I will see you in the next lecture.